And let's start the slideshow from the current slide. So, as Brian was saying just a few minutes ago, we're in chapter, well, you didn't say this part, I'll say this part. We're in chapter 19. Now, if we can get before 1 o'clock, is that right? Yeah, before 1 o'clock, the rest of 19 covered. I'm not going to push it, but if we can, then we'll have time to do the lab for chapter 19 and then do the test in chapter 18. Okay? If we don't get that far, no. Did we ever do the lab for 18? No, we didn't. That's right. So, yeah, you got it. That's it. Okay. So, at 1 o'clock, we stop the class wherever we are in chapter 19. Then we do the lab for 18, and y'all have that already. And then we come back, and y'all can take the test on 18. And then next time, on Tuesday, I'm pretty certain we're going to finish 19 in plenty of time, and then we'll have a chance for the lab for that one as well. I don't think we'll finish 19 today, but if we do, then we could even have the test on 19 next time, but I don't think that's likely to happen. Also, I think there's a bit more, too much chapter to do in only about 40 minutes, 45 minutes or something like that.
What's the last chapter will be?
I'm sorry?
What's our last chapter?
We do 19 and 20. We skip 21 and 22. We do 23. If we have a chance, we'll do 24. Doesn't look likely now because we lost the first day of class, period, because we thought it was going to cancel. And then we lost 4th of July. And we lost the time I had to go to New Orleans. So, I don't know. Yeah, we'll do 19. I'm pretty sure we'll get 20 done. And then we'll do 23 if there's time. And if we don't get to 24, that'll be fine. It's the oceanography part, Earth's Waters, it's a fun, good chapter, but if we don't get there, we won't. But we may get started in it and just not have a chance to finish it. All right, good deal. So that's it. We'll get going on 19 now. When we get to 1 o'clock or shortly after 1, we'll do the lab part for chapter 18. And once we get that done, then we'll come back here and do the test on chapter 18, unless you want to stay where we are. That's up to you. And then you'll probably get to leave early today because of that, because the lab's not going to take that long to do. And then we will, next time, most certainly finish 19. If we don't today, which I don't think we will. Excuse me. And we'll finish 19, have the lab on 19, and then Thursday we'll be into 20 by then, I'm pretty sure, and doubt if we'll have time for the lab on 20, we might, we'll see, and then we'll have the test on 19 on Thursday. I mean, Tuesday, if I want to. No, Thursday of next week, that's what I'm going to say. All right, and then I think we've got one more week of class, and then finals, is that right? Sounds about right. Okay. Any other questions then? Can't think of any other changes to my schedule. I do have coming up, not next week, but the following week, I think, a meeting on the Birmingham campus. I'm pretty sure it's either a Tuesday or a Thursday, but I think it's in the morning, so I don't think it'll bother this class. The worst it'll do is make us a few minutes late getting started. Just depends on how long the meeting goes, but it's something they require us to do. So. Crazy summers. Okay. So no questions, anything we've gone through so far? Okay. Last time we talked about, or this chapter is talking about, what was one of the processes we're talking about that says everything that's being done, we've done before, has happened before. Principle of uniformity. Dystrophism follows that, and that basically is how things are acting now as they have in the past. And the earth is always changing, always changing. One of those ways it changed before we started in the faulting was what? Folding, exactly. Folding can be folded up or folded down, okay? Now we're talking about faulting as opposed to folding. Oh, let me back up a little more. We talked about the forces that cause these things, and what are they called? There are two S words. In fact, they're both STR words. One was the force and one's the result of the force.
Stress.
Stress is the force. Strain is the result of the force. So that's what we're talking about here. The stresses are either compressional stresses, tensional stresses, or shear stresses. And the strains are some of this stuff. You either have no reaction, you have elastic reaction with rebound, you have plastic reaction, or you have fracture or rupture. The folding is basically plastic strain, because the especially sedimentary rock that was in nice horizontal layers has now been folded up or folded down, so that is a plastic strain. Faulting, on the other hand, is dealing with the rupture, the break, the fractures. And what faults are, they're produced by relative movement on opposite sides of a rock. Now there's one little deal here. I want to make sure you see it before we go too far with it. Rock layers do not always respond to stress by folding. Okay? They may or not. Rocks near the surface are cooler, under less pressure, so they tend to be more brittle. A sudden stress on those rocks may reach the rupture point pretty quickly. If there is breaking of a rock, now this is on page 485, that sentence there, if there is breaking on a rock without a relative displacement on either side of the break, that has a special name. It creates a crack, and that crack is called a joint. That crack is called a joint. A joint looks sort of like a fault, except with a fault you have displacement. With a joint you just have a break but no displacement. That's the difference. So a fault is produced by relative movement on opposite sides of a crack, so you do have displacement. Now, most of that movement is up and down. I've been saying it like this, but it's mostly an up and down. So, this is a pictorial example. Here is an actual example of a fault. There's the fault. The actual rock ruptured, it broke, it has a seam in it. This is a cleaned up version of someone's picture of it, but that's nice and smooth. Most of the time it's not that smooth, but it's a surprisingly straight and smooth, okay? To me it is anyway. And you'll see some things go up and some things go down. Now, the lower part of that, the part below the angle, that's called the footwall. The mass of rock below the fault. Most of the time you don't have faults that are up and down. They're always at some sort of an angle. Okay? If you're below the fault, below the fault, then that's the footwall. There's the footwall, there's the footwall. The hanging wall is the mass above the fault. Here or here. There's the hanging wall. Now, seems sort of funny, the footwall either has moved up or the hanging wall more likely has moved down in these two pictures. Okay? The fault plane is that surface between the footwall and the hanging wall. where the crack, the rupture, the fracture actually occurred. Okay? So that's what we mean by fault. Always, generally at some sort of angle, below the fracture plane, fault plane, you have the footwall. Above it, you have the hanging wall. Even if that hanging wall isn't hanging too well, it slid down the footwall. It's still called the hanging wall. Okay? Any questions on that? Now, as always, 3 types of faults. Okay, classes of faults. They always classify things. We're going to start with 2 major, and then we'll do 1 subdivided. The first is called the normal fault. Why they call it normal, I'm not sure. In this case, the hanging wall has moved down relative to the footwall. Those last 2 figures we saw, those were both hanging walls going down, so those were normal faults. Now, there can be these related features. And don't worry about them. The book seems to like them. I don't think I've ever used the term anywhere but in this course. And I'm trying to see even if, yeah, they have the same figure in the thing. But don't worry about this, just in case so you know it, okay? Related features. If you have a block that's surrounded by normal faults, okay, like this, okay? This is a normal fault because the hanging wall slid down. This is a normal fault because the hanging wall slid down. So if you have a block surrounded by normal faults that drops down, the hanging wall dropped down between the 2 normal faults, that's called a gradient. Never use that term anywhere else except here. If, however, you have 2 normal faults on either side, and on either side the hanging walls fell down, leaving the footwall raised up, the block is surrounded by normal faults is uplifted, really the other 2 drop down, but it appears to be uplifted, then that's called a horse. Never have I used, and probably will use these terms anywhere except in this course. So graven, I don't know, think of it toward the ground, it went down. The horse is sort of like you hoisted it up. I don't know. Any way you can think of remembering those. But don't worry, I'm not even going to test you on them, but that's the difference here. Now, you don't always have this feature, but you do occasionally will see something like that. And you might say, why in the world is that like that? Well, it's probably because you have a fault. In fact, 2 normal faults on either side. They were like this, and the hanging wall dropped down. Then you had a, that was a graven. If they were like this, and the hanging walls fell down on either side, which made it appear that the footwall was raised up, then that's a horse. Now, I want to point something out to you. They're showing arrows here. What do you reckon those arrows represent? The what?
I guess outward tension.
What?
Outward tension.
Okay, very good. In fact, you use the term perfectly there. Okay? These are your stresses, and all 3 of these are stresses. Are tensional stresses because it is being pulled away. Okay? The normal faults always result from tensional stresses because that leaves the footwall, the hanging wall is always falling down, meaning you had tensional stresses that pulled them in that direction. So there's another feature they didn't say here, but that is always the case. The normal faults are always caused by tensional stresses. Very good. Okay? Other faults. Normal fault, then we have a reverse fault. Well, if it's not a normal fault, the reverse fault would be that the hanging wall is moved up relative to the footwall, like this. The hanging wall here, the footwall is always on the lower side, the hanging wall has moved up relative. And guess what kind of stresses create that? Compressional stresses. Those who have to be pushing down, that pushes the hanging wall up the footwall. Not an easy thing to do, but it does. So there's the reverse fall. Hanging wall moved up, result of horizontal compressional stresses as opposed to normal faults, which are tensional stresses. There is another kind, but this is a kind of a reverse fault. It's called a thrust fault. In this case, it's a reverse fault, but it's a very low angle fault plane, meaning that it slides up ever so gradually, and you don't have a big cliff or something like this that you see in the others, but you hardly see any motion at all. Maybe the motion happens slowly over time, and you have a big difference here, but usually this is smoothed out more than that does, okay? And that's called a thrust fault. A reverse fault, which results in compressional stresses, but it's a very low angle fault plane, so you don't notice it so much. Now, the faults provide information on the stresses producing the formation. If they're thrust faults, reverse faults, then you have compressional forces, stresses. If they're normal faults, that means you had tensional stresses. Okay, so those are your faults. Not my fault, never mind, no, I'm just kidding. Okay, they have some great looking pictures here. I am not absolutely certain why they have them in this location, okay? Figure 19.8, just make sure I haven't skipped any. Columnar jointing forms at right angles to the surface as basalt cools. So those are samples of joints where you don't have relative motion at the breakage. That's a joint. And those are pretty incredible. And by the way, that's basalt, which meant the odds are this was probably underwater at one time. Not always, but it could have been. And the A is called the Devil's Post Pile. I don't know how the devil gets in on this, but he's in on it in a lot of ways. I don't know why. But that's the San Joaquin River in California. And then the B one that's there is the Devil's Tower. That's what I said. There he is again, Wyoming. And that, I'm pretty sure, is one that you will run into in lab, if not the next lab, the following lab, okay? You'll run into and see the Devil's Tower. I believe that's the one in a later lab. Okay, yeah.
Like this, I guess the movement of faults, do they create like land formations like you see at the national parks in Utah, like arches or?
Yes, they can. Now, some of those arches are done by erosion, but others are caused by the stresses and the result of their strains as a result of the stresses. Yeah, you're absolutely right. In fact, I've started doing it pretty frequently now. Dr. Bryant, who teaches physics here, his car, he's been having a lot of car trouble, and he's been depending on his, I think it's a niece or somebody to give him rides here, and I think she doesn't really want to come back real late and pick him up again, so he says, it's kind of in my way home, so I've been giving him a ride home, and I noticed he lives near Oak Mountain State Park, this side of it, but you got the is it Double Oak Mountain or something there, and then you have Shades Mountain and stuff. And as I drive over those, I think, now is this a folded mountain? Is this a fault mountain? You know, what caused this? But these are causing most of the, like you said, the landforms, the features that we see. Yes, it's being caused by this kind of stuff. So yeah, the answer to your question, most definitely so. Now there is one in the text. I said you don't usually, but there's one figure 19.9, and this is a new one because this one I don't think was in the old text. The A one up there is pretty clear. What kind of fault is that? Well, no, it's not real clear, is it? I guess it is. That would be a reverse fault because it looks like the hanging wall has been pushed up over the footwall because the hanging wall is higher. Okay? Now, look at figure 19.9b. A photo of a fault near Kingman, Arizona, showing how the hanging wall is moved relative to the footwall. And I look at that and say, which is which? Because that's almost a vertical fault. The only thing that differs is that right near the center of it, it sort of goes like this, okay? So the footwall would be the one on the left, and the hanging wall would be on the right, and the hanging wall has dropped, so what kind of fault would that be? You can't see it here, it's the one in the book. You may not have your book. That would be a normal fault, I think. But that's almost a vertical fault, right after I said. You don't usually have vertical faults, but there they have a picture of one. Okay. Example 19.1, and again, it's sort of like they make these things up. A graben is bounded on the east and west by two normal faults. Yeah, that's how you define them. A fault plane on the west has a slope of 1.3 meters per meters to the east, and the plane on the eastern fault slopes 1.8 meters per meter to the west. The sedimentary layers cut by the faults have been displaced 31 meters. How much extension has occurred? It's just a math problem, and it's not a particularly practical math problem either, but it's there. But if that interests you, it's worth looking at and seeing how they did the calculations. Okay. Any further questions on faults or folds or stresses or strains? We're now moving to the next topic in the chapter, 19.3, earthquakes. This is always a great interest. And let's see, I can't think of any really recently. The last I remember hearing of was the one in Montana, I believe it was about 2 or 3 weeks ago. Not a very major one, so as Montana is fairly sparsely populated. It sounded like it was pretty powerful, but there was no major damage that I remember hearing about. Certainly no loss of life or even injuries or anything from it. People said it woke them up in the middle of the night, but that's about it. So what is an earthquake? Well, quake means moving, shaking, vibrating, upheaval of the ground. Something is going on, generally pretty far under the ground, that you feel the effects on the surface. The result from a sudden release of energy from stress on rocks. And again, there we have it. Stress is the forces. And the rocks are having trouble passing each other, though the plates are moving, but they're hung up on each other, and when one of them finally breaks, then you have the quake, the sudden release of energy from the stress on the rock. You had deformation, it had been elastic, mostly elastic, and then suddenly it went to fracture. And that's what caused the earthquake. Now, from the shaking and the vibrating, those vibrations are what we call the seismic waves. What do we measure these with? Seismometers, measuring the seismic waves. Now remember, we've already talked about 3 types of waves. What were they? S waves, you said? Yeah, that was meaning?
Shear.
Yes, shear waves. Another thing that starts with S? No, that one's the 3rd type. Secondary wave. The shear waves are secondary waves. They're also called, most of it. And what was the other one? P waves. What are the two words for P? P words? It's not secondary, it's primary and pressure waves, okay? Those are the longitudinal waves going in the same direction. The other one I was trying to think of was the transverse waves. That's also the secondary or the shear waves. And then the third was the surface waves, which basically is sort of like a water wave. You have up and down movement, right and left movement, it's just all. They're the slowest of the waves, okay? But those vibrations are your seismic waves, measured by seismographs. Most occur along fault planes when one side is displaced with respect to the other, okay? It could be normal faults, reverse faults, whatever, but you have a fault plane there, something gives way, okay? And you create a fault plane, or the fault plane is enhanced. One side is displaced with respect to the other. Now, what are the causes? We've been talking about it. One theory is what they call elastic rebound theory. Maybe there wasn't actually a rupture or a fracture of the rock. The two plates are pressed very tightly together. The friction keeps them from moving. The stress builds up until the friction of rock, and then they say, so this would be rebound until the friction of the rock rupture strength is overcome and it actually breaks. Well, when it breaks, then the rest of the rocks go back to the normal original thing. That would be the elastic rebound. But it still involves rupture or fracture of a rock. The stressed rock snaps suddenly into a new position. So the rupture occurs that relieves the pressure, and then the other rocks that were also under that pressure step suddenly to a new position. That's the elastic rebound. Okay? Now, that's a theory. I don't know if anyone has actually gotten enough data to show, yes, this is truly what happens. But here is one of the most famous of our fault lines, the San Andreas Fault. Have you all heard of this before? Yeah, most people have. It goes smack dab through San Francisco, okay? Back in, 1903, 7, sometime in there, they had a major earthquake in San Francisco. San Francisco, remember, had been the boom town, 1849, the 49ers, you know, the gold rush in California. It was just, booming out there. And San Francisco had grown very suddenly to a pretty major city. And frankly, this is just my opinion, the whole reason you got all this San Francisco Bay here is probably because of repeated activity there along that fault line, and you have erosion and other things that have contributed to the bay being formed, okay? I may be wrong on that, but that's my guess. Now, that fault line goes all the way up and down. This is the Pacific plate here, the North American plate there. There are definitely some issues with the faults along that line. Now, San Francisco had another fairly big plate. It was called the World Series plate. Do y'all remember that one? The San Francisco Giants were playing the Oakland Athletics. Oakland had won the American League Championship. San Francisco won the National League Championship. So there, it was called the Bay Bridge Series. They just went back and forth. Oakland's on this side of the bay, and then San Francisco's on that side of the bay. And they just went back and forth playing the games. Yeah.
There's a lot of footage of that on YouTube, like news footage when it happened.
Oh, really?
In this famous footage, they show a car driving on the bridge, and it goes down because it's on the top level.
Right.
And it drops down.
Yeah.
And it shows like people walking in and all that stuff.
Yeah.
When was this? 89.
October 89, during the World Series.
Yeah,
I think there was a game going on.
Yeah, it actually shows.
I think it was in San Francisco, huh?
It shows them stopping the game.
Right.
In the middle because it's starting to happen.
Yeah. Yeah.
I don't remember. I was like 6 when it happened. I just saw it on YouTube. Now I remember news to
I was working for Southern Research at the time, and we were at some meetings down in Tallahassee, Florida, meeting with some architects, and we were developing some of the code that we're writing about radon resistant construction, you know, and we were working down there on that, and we went to a place for supper, and there was a TV going on, and everybody stopped everything and were watching the news of the earthquake during the World Series game. Yeah, it was, I was a little more than 6, but yeah, I would remember that pretty well. So, and then I think, I can't remember which side of it was, I think a couple of years later, but they said not related to it, Los Angeles had a pretty major earthquake. 94, okay. And you're absolutely right. Of course, there's the Golden Gate Bridge that goes across the, it was called the Bay Bridge Tunnel. It's a bridge tunnel. It comes across here. Now, this is hard to see here. There's an island right in the middle, or kind of in the middle, called Yerba Buena Island. It means nice herbs, you know, good herbs, you know, good grasses and things like that. It's a tall mountainous thing just right in the middle of the bay. They dug a tunnel through the mountain on the island, and then on either side they had the Bay Bridge. So the Bay Bridge Tunnel, okay. And the Bay Bridge was eastbound traffic going one way, westbound the other way, and they were on top of each other. And I think there may have even been a rail line underneath both of them. So that was the Bay Bridge Tunnel, and when the earthquake happened, some of those plates from the upper, what you were describing, collapsed, and cars fell down onto the other, and others got crushed underneath. It was not a pretty picture, and boy, you talk about gridlock there for weeks, because that was the main way to get back and forth there. See, Golden Gate goes across this way, Northern California Southern. This is the peninsula where San Francisco is, and this is where Salinas and some of those other towns are up here. But Oakland and all the rest is this way. So the Bay Bridge was the main east-west way to get in. After that, they had to drive all the way around or up to here. It was really, they had very few options there, and it was a major, major catastrophe. And then what was it?
Sinkholes.
What's that?
Something like this what causes sinkholes?
It could perhaps. Most of the time a sinkhole is caused by, remember when I talked about the Grady ponds and things like that, usually limestone or chalk deposits, and either water washes them out or they oxidize away and the land subsides. That's most of what I think causes most of the sinkholes, especially in this area. Now, just over here, Powder Plant Road.
Yeah, I know what you're.
Okay.
That little trailer park.
I guess so. I don't know. I've
There
heard
was a
about it. I've
trailer
never
park
seen
there
it.
and started sinking.
Yeah. And what I heard was the cause for that. They have a big operation back there that produce gravel and I think maybe cement, mortar, concrete, all sorts of stuff back there. And they use a lot of water to separate stuff. The sands, the silts, the clays, the gravel, and other things, the river rock and things. Back when we were working on our patios and that kind of stuff, I had a pickup truck at the time, and I would sometimes leave here, go over there, get a load of gravel or sand or whatever, and then take it home and work on it that weekend. So that got to be too much of a habit. It was backbreaking, but we did that, and evidently they used so much water separating things and making the mortar mix and that kind of stuff that they washed out stuff. So it may not have been actually limestone, but just washing things out, and then you have sinkholes and drops. So we have a neighbor, I mean, just next door neighbor in their front yard, it's just a hole that keeps showing up. We fill it up with soil. I've carried some over when we dug out our patio and filled it up, and within a few years, went right back down again. And I don't know if it's the sewer system underneath is washing the soil out. I don't know what's doing it, or just a natural stream, or if they have limestone that's subsiding. Last thing, they have a young kid now that people are living there now, and he used to collect acorns from all over the neighborhood and fill the thing with acorns. And for some reason, it seems like it's not subsiding as much. I think it just reached its max, but he used to fill that thing with acorns. I thought, well, they're not going to last too long, but good to level it out.
We have, I have 5 acres of land. We have a creek that runs through our property. And it has these big, about the size of this book, it has these really big, thin rocks on the creek, and they're beautiful. I have people all the time that want to pull their truck down there and get loads of those rocks out of the creek. I've given so many of those rocks away, and they still there. I mean, I don't know if the water, I don't know what happens, but you can't give them all. It's like a new, whole new thing.
Are they like flagstone? Nice flat? Yeah, I can imagine people are. What's that?
They do all kind of.
Yeah, we did our patio with flagstone, and it was a hard job, but it really made a good looking product.
Yeah, they're very pretty. I don't know if the water uncovers more.
Yeah, that's what I'm guessing is happening. I had friends who lived in Nebraska when I was in grad school up there. They bought a place, and they were away for most of the summer, so I house sat for them, which was nice for me. But while I was there, I decided I knew they wanted to start a garden, so I started digging up a place in the backyard for a garden. And that's mostly, Nebraska is the place where the glaciers pretty much advanced to there and then retreated. So a lot of really good, thick topsoil from Canada was brought down and then deposited there where the glaciers melted. But they also left bunches of rock there too. So when I was digging there, I ran into a lot of rocks, and I would pull them out and put them around the edges, you know. And the first year, you know, especially you saw, I had a big garden there. Had a pretty good garden that first summer. And then a few years later, a year or two later, I happened to ask Roger, I said, how's your garden doing? He said, same thing you did. He said, seems like all I can grow is rocks. He would take them out and move them around and stuff, and the next year there it seemed like more just popped up, you know, whereas really the soil was eroding, you know, somewhat, and they were coming. He said, I'm growing rocks. Well, Los Angeles, then later, like you said, what, 5 years later, in 94, had a really major earthquake, and lots of the interstate traffic and overpasses and stuff like that, they fell down and stuff, and it probably wasn't as deadly as the one in San Francisco, but it still caused a lot of travel.
So thankfully, both I think the one that happened in Los Angeles happened on Holiday.
Yeah.
On Martin Luther King Day.
That's right.
So
Martin Luther King Day.
Yes,
that sounds right.
So
yeah.
Was traffic.
Was as much traffic.
And
Yeah.
then the other one, since it was the World Series was going on, I don't think there was as much traffic either.
Yeah, exactly, because the games were actually underway. If it had been before or after, it could have been really, really costly. But you know, the bridge was still going the same. But so yeah, it's we sort of lucked out there. Now, I want to propose something to you. I don't know if this is true or not, but notice where this goes. What's below? James is here. So all of our Y chromosomes have made it. Poor Amber is out of town this week, I think. Okay. Notice here, what is south of California? Mexico. Okay. And this, I think, is Tijuana State right there. Okay. I'm gonna get my good old globe, but I don't know if you'll be able to see it as well as. Okay. Picture that, see where the quake goes? That place in between, it looks like Arizona dropped down more than it does in reality. But there's the Baja Peninsula there, right south there, just follow that line, and just below that is called the Gulf of California. My guess, that is right along the fault line. Why in the world Baja California is a little peninsula there, but that's exactly, it looks like to me, exactly where that fault line goes. So there's probably been enough activity along there, maybe long time in the past, and it erupted, and then probably things eroded away or whatever, and you wound up with a big gulf there. Now, the part I can't understand on that, and I would have talked about this in a later chapter, but we may not get there. Here this little thin peninsula is, Baja Peninsula. Have y'all heard anything about that? They have road races there and things like that. It's the Baja California Peninsula. It's in Mexico, okay? And this is called the Gulf of California here, but that's in Mexico. This is one of the driest places on Earth. It's surrounded with water here, and there, and it's dry. Really dry. Like, oh my God, you know, it just happens to be.
Is that where they had the salt flats?
Yeah, well, some of them. There are salt flats also in New Mexico, I believe it is, where they do drag racing and speed trials and things like that. So, right beyond here is the Gulf of California, and I just can't help but think there's a reason it's on the fault line. Something is related, interacted there.
And one day we're gonna have a giant Long Island.
What's that?
So you think one day we're gonna have a giant Long Island?
I don't know. It could be. Yeah. There have been all sorts of jokes about California. Why doesn't it just fall off and go into the ocean and leave us alone? That kind of stuff. Okay. Now, this is one of the most incredible pictures I think I've ever seen. I think this must have followed the. When did you say that quake was in the World Series quake? 89. There must have been something that happened back in 79, because this picture here, absolutely unbelievable. This is on the San Andreas Fault. Some farmer had planted straight rows of whatever it was he was planting there. This must be early spring or something. And then there must have been a fairly significant quake, and it's a transformed boundary, so the sliding was this way. And look, his roads aren't anywhere close to straight anymore. I've never seen anything as marked as that, because there you have the roads going this way, and they got them off base. This is sort of showing what's going on there in a very strange sense. You have either side of the fault line, you have the stresses, but they're not directly against each other. They're offset. It's a transformed boundary. One plate's going this way, one's going this way, and the stresses are there. And right now, there probably is no deformation early on when the stresses were pretty small. Now, I've never seen this happen. This is just someone's artist concept. But after a while, you could have some plastic kind of stresses here. Again, this is the artist thing. You wouldn't actually have that. But then when something snaps, an earthquake somewhere way down there, and then you have the whole things give way, then you have the fault. Here it was folding, you might say. Here it was actually a fault. And most of the time we talk about it this way, but that's what's going on here. And again, this is grossly over magnified. You don't have a whole lane of road, that much. You have a few inches of movement. You don't have 8 feet of movement like they show here. It would be just a few inches of movement. Okay. But it's a sudden snap back into place and everything gets distorted a little bit. Okay? So how do we locate and measure earthquakes? Let's see. Man, I did too much talking. That's probably a good place to stop for the lab, don't you think? It's right at 1 o'clock. If the lab goes 1 to 3, then the test 3 to 3:30. You'll be through with the lab way before 3 o'clock. So you want to try to get a little more in or not? Huh? Do a little more? Okay, we'll go maybe one more section. All right. Locating and measuring the quake. Where the quake actually happens. And this is usually down deep. Some of them are shallow deep, some of them are medium deep, and some of them are deep, okay? That is the focus of the earthquake. The actual origin of that fracture of the rock, whatever gave way, that is the focus. Now, you never hear them talk about the focus, do you? If you've ever heard them refer to earthquakes, they'll say, so many miles from the epicenter. The epicenter is not the center of the earthquake. The epicenter is the location of the Earth's surface directly above the focus. The earthquake is always happening somewhere down there, but wherever that is on the surface of the Earth above that, that's what we call the epicenter. Okay? So there is a difference in depth between these two. This is directly above that, but this one's way deep in the Earth, this one's on the surface. Okay, and as I asked earlier, how do we measure these things? A device called a seismograph. Graph means to measure, basically, or to draw or to measure the seismic waves. It's an instrument used to detect and measure the strength of the earthquakes. Okay, and again, what are the 3 kinds of waves we have? P waves, which are primary pressure waves, and they're longitudinal waves, meaning the motion is in the same direction of the wave propagation. The second are the S waves, which stand for second or shear, okay? Those are transverse waves, where the movement is perpendicular to the propagation of the wave. And then the surface wave is sort of up and down. That's what happens once the waves, whichever waves reach the surface, then those are the surface waves. Okay? What we covered in the earlier chapter. So here's a picture that illustrates this. The fault occurred. The rupture occurred. What kind of fault would this be? The what? Which one? The walls are either, here's a wall and there's a wall. Which one's the foot wall? One on the left or one on the right?
Right.
The right is the hanging wall. The foot wall is the one below the plate. So this is the foot wall. And this is the hanging wall. The hanging wall has gone down. So what kind of fault is that? Normal. That's the normal. Normal is for it to go that way. Remember, tensional. Okay? Now, the earthquake occurred right there. Everything had been hunky-dory, but there's a lot of pressure there, and then when it did give way, that's where the break occurred. That's where the fracture occurred. Now, this is a gross exaggeration. It's usually not that big. Way, way down deep, that's the focus. Above that, you have the epicenter. This is the epicenter. Go straight up from the focus, and that's the epicenter. On the surface of the Earth, where is that center? Okay. All right. Now, here's a picture of a seismograph. This thing, this part, is solidly embedded in the bedrock. I mean, it is there, okay? And they are pretty much fixed. Now, when you have movement of the ground, here you have a big mass, a heavy weight on this thing that's connected to the pin. There's a wire that keeps it in the right position, but when you have movement of the ground, its inertia tries to keep it in place, whereas the ground is doing like this, so you get the, as long as things are normal, it just does like this. But then when you have an earthquake, you get that kind of motion. You can see it, obvious, okay? And not just that, you'll see the P waves come, and then later you'll see the S waves, and then you'll see the surface waves. You'll see them coming after each other, and that difference in time, we'll talk about that later, tells you how far you are from the, probably from the epicenter, but I think it would be more precise to say from the focus, okay? And that's basically what the seismograph is. Your paper is always turning, so you'll go through lots of rolls of paper with almost nothing going on. Now, what else will set these off? Oh, and by the way, internationally, countries don't usually get along too well, always. There's always somebody mad at somebody else, or little skirmishes or wars or embargoes or trades or wars or something going on. But two things have been done, both are scientific type things, that have been phenomenally successful across the entire planet. Countries that don't like each other, can't stand each other, they've done these two things extraordinarily well and cooperated so well. Scientists tend to get along, okay? It's the politicians that don't, okay? And the scientists that do tsunamis, all the countries that have borders on waters, they cooperate, they have their, I think there's actually a name for that, stations out there, and they communicate to each other really, really well. If there ever is a tsunami, everyone lets everyone else close by know immediately. And that has been one of the most successful international partnerships that we've had. Countries that can't stand each other still contribute together, coordinate. And the second is seismographs. Every country in the world has them. They have them set up, they're probably calibrated well, they agree to do everything right with them, and when they sense movement, they let everybody know, and everybody then watches for theirs, and the measuring that from all these different areas of the world, you can then pinpoint exactly where that epicenter was, okay? So two things that have been done really well is the cooperation of seismography and also with tsunami. Okay. Seismic data, okay? Now let me know if when you want to stop and start having loud, like I said. Have you already started on your questions? Okay. You have? Okay. Good. If you know, it'll help you some on the test, but the other thing is that is a big portion of this lab, more than half of it. So what are the seismic data? Well, we've already said the P waves travel faster than the S waves, okay? What's another difference between P waves and S waves? Not really dealing with it here, but what's another big difference between P waves and S waves, especially about the time? This is how we know stuff about the center of the Earth.
One of them travel through?
Yes, the P waves will go through solids and liquids, and the S waves will only go through solids. So that tells us something about the core of the Earth that we wouldn't have known otherwise. That's not got anything. It is seismic data, but that's another issue. So the P waves travel faster. Therefore, the difference in their arrival times correlates to how far you are from the earthquake. Because let's say that when we're heading to the planetarium, Ricky kept up with me pretty well. Every now and then we got sort of separated. Now, if we had taken off and gone, and I had driven 5 miles an hour faster than Ricky, the longer we drove, the further we would be apart, right? For every hour, I'd be another 5 miles ahead of him, right? Same thing happens here. The P waves travel faster than the S waves at a fixed rate, so when they're at a seismic station and measure that first P wave, and then they start looking for the S waves, and when they finally see the S wave, the difference there tells them how far they are from the earthquake. That's exactly how they tell. That difference in arrival time correlates to the distance from the earthquake. Now, what they do then, and here's the illustration of it, here's the picture of that. Here is your distance from the earthquake, and here's the time of arrival. I would have thought they would have reversed these, but it's okay. If the time of first arrival of the P wave is this time, and then you get your S wave at that time, that difference in time correlates to how far you are from the center of the earthquake. Okay? And when it's here, you're this far. So that how long it took time-wise correlates to how far you are apart from the earthquake. Okay? Now, so what you get when you measure that at your station and see that you're 150 kilometers from the center of the earthquake, what you can do, because of that time difference, you can draw a circle. You're right here, but you know the earthquake was somewhere on the boundary of that circle, 150 kilometers away. Well, some other station down here, when they did their differences, they were 200. They were up here. So they were 200 kilometers from. So they draw a circle there. There's their center. They draw a circle around it. So now we know with those two pieces of data, the earthquake was either here or there, but we don't know which. When the third station comes in, and their difference was like down here, and the time difference was here, so they measure it and say, that means we were that far from the earthquake, 100 kilometers from the earthquake. They draw a circle around their position. Bingo! I can't say that in Alabama, but there we are. That's where the earthquake was. The epicenter of the earthquake was right there. You have to have 3 stations reporting. Now, most of the time they're not that close together, but 100 kilometers is 60 miles. I mean, they're not every 60 miles, but they did it for illustrative purposes. Okay, so the triangulation is used to pinpoint the epicenter, and then go deep, and you'll get the focus of the earthquake. Epicenter is where it is on the surface. Focus where it is underground. Okay. Want to go another or not? Huh? I can't hear. Huh?
I'm ready for next time.
Start the lab? Okay. We will start next time then with classification of the earthquakes. Okay? And this basically is on the beginning, it's sort of deep, toward the bottom of page 490. It's actually where the text begins on 490. You have some real nifty pictures there. This new text has some better figures than the old one did. And they show the how they locate and how the P waves and S waves travel there. And they actually have actual seismograph pictures of quakes. I think that's pretty good. The old edition had one, but they didn't show it on the slide set. This one's even better. Okay? All right, so pay attention to that. We will pick up from there next time. Okay. We'll probably go down to 259 if there's not a class down there. Okay. Okay. All right. All of you have your labs, right? I'm going to go on and shut down. Sorry, Amber, I forgot to turn the sound on again. We had a few questions about what are igneous rock, what's the difference between granite and basalt. We have our setup. We had a balance that we used to measure mass with. We had an overflow can to catch the water so we could determine volume. Graduated cylinder to measure the volume of water. Ring stand and ring to hold the original in. A beaker to catch the extra. A granite specimen and a basalt specimen. We talked about the differences between those. Then we did the measurements. The first thing is use the balance to find the mass of a basaltic rock, and someone tell me what we got.
161 grams.
161 grams. Okay? Then we filled the beaker on the ring stand till Ricky was doing it literally till it was overflowing. I mean, you could see a crust on the surface on the top. That was the surface tension of water holding it there, and had it as full as it could possibly be, and then very slowly put the 4 pieces of basalt into the water, trying not to spill any. A little bit may have spilled, but not too much. And then I believe it was Brian who did the volume measurement. And what did you get for the volume of the granite?
51 centimeters square cubic.
51 cubic centimeters. It was measured in milliliters, but a milliliter is the same as a cubic centimeter. Okay? And then we did the same thing for the granite. It was a much bigger piece of granite. What do we have for the mass of the granite? 442.5 grams of granite. And then we very slowly and carefully lowered that into the beaker of water that was, again, full to the top, and caught the overflow, poured the overflow back into an empty beaker, and then poured that into the graduated cylinder. And what do we get as the volume of the water displaced by the granite?
180 centimeters.
180 cubic centimeters. Now we're going for our calculators, okay? And to get the density of basalt, look at your units, and they tell you. It's grams per cubic centimeter, so you divide, say again?
Divided by gram.
Divide the mass by the volume. Put the mass in first, divided by volume. Say again?
So 3.16.
3.16, is that what you got?
I got 3.1568.
Okay, we can round to 3. Okay. Too many digits. TMD, too much digits. Okay. Too many digits there. I think the 3 will do. What did it say?
3.16.
3.16 gram per cubic centimeter. That's the density of the basalt. Now, just looking at how much granite we had, do you think there's any way we're going to get a smaller density for granite? Look how big that piece of granite was.
Yeah,
But the volume was bigger too, so when you divide, what do you get? Mass divided by volume?
2.46.
2.46 grams per cubic centimeter. Sure enough, the basalt is denser than the granite. Okay? Makes sense? That was our wet lab, literally. Okay? We actually did a wet lab. Now, that was 246 points worth right there. You've got 4 more questions that you can do. So why don't you work on those, and if you have questions of me, be sure to ask. Okay? So you be working on those. You can work among yourselves, discuss it among yourselves, whatever. If you have doubt or question, ask me.
Results.
Meanwhile, I'll be taking the lab down. And I think I'll even move my computer away from where the water was, just to get it safer. I may just turn off this for right. All right. We found in page 461 in chapter 18, actually, comparative sampling. We had granite type rock on page 461, right-hand column, that middle paragraph that starts comparative sampling. We found the density of granite type rock to be about 2.7 grams per cubic centimeter, and we got 2.46, or about 2.5, so not far off. Okay, and then a little bit, the 2 lines further, it said, oceanic crust, on the other hand, is made up of basaltic rock with a density of about
3.0.
And what do we get?
3.16.
Look at that. Not bad, huh? Right in the same ballpark. Okay? So, pretty good experiment, you guys. Okay. So, I'm going to put it back on. All right, there was a question on number 1. In what ways, this is the questions after you've done the calculations on page 338. Then go back to 336 and answer the result questions. In what ways do igneous rocks have different properties, and what were some of those? Say again? Texture or grain size. Some are coarse, some are fine grain. Very good. Number 2. Color. Some are dark and some are light. Number 3. Density. Some are more dense and some are less dense than others. Okay? Number 2, explain the theoretical process or processes responsible for reducing the different properties of igneous rock. What was the first one you said, color or texture? Texture. What was the theoretical process that produced the different textures?
Cooling process.
Okay, the cooling rate, and what did that sort of depend on?
Slow cooling produces coarse grain.
Slow cooling produced coarse grain, and rapid cooling produced fine grain. What determined then the cooling rate? How deep it was. Most of the time your, help me with the term, intrusive igneous rock cooled more slowly, so it had larger grain size, and the extrusive igneous rock, those near the surface, usually had smaller grain size. Very good. So that was grain size. What was the next one? Color. Okay. What theoretical processes could be responsible for producing different color in igneous rock?
Presence of iron.
Presence of iron. Excellent. Okay. Because usually the darker color rocks are high in iron content. The lighter color rocks are low in iron content. And iron is one of the heavier minerals in the igneous rock. So that would contribute. And what was the third one? Density. And most of the time, and that's what I was just saying actually, in the wrong place, the higher iron content usually is more dense. And what do we notice between basalt and granite? Which was darker? Basalt. So it probably had higher iron content. So we expected a larger density, and sure enough, we got it. Okay, number 3. According to the experimental evidence of this investigation, what you just did, propose an explanation for the observation that the bulk of the Earth's continents are granites, and the basalt is found mostly in the Earth's interior, or oceanic crust or interior. Why would that be the case? Propose an explanation.
Because granite comes from deeper.
Okay.
Because the cooling process is slower because the heat has nowhere to escape.
Okay, and that's pretty much true. Think of this. Remember that, what's the guy's name? I want to say Boeing. That's not it. The table that he had. We turn back and look at it. Say again?
Mohs table?
No, that's a hardness table. That's one. Here it is. Bowens. Okay, Bowens are they call it reaction series. Okay, the heavier, higher iron content usually comes out at higher temperatures, and then the lower iron content comes out at lower temperatures. So the interior basaltic rock, the higher iron content. Now, if it's the bottom of the ocean, that's what makes it fine grain because it cools rapidly. But that happens generally before the lower iron content, as in the quartzy type materials. So therefore, that would almost do it, wouldn't it? Propose an explanation for the observation that the bulk of the world's continents high up are granite, and that basalt is found mostly either in the Earth's oceanic crust or in the interior, and that's because the iron minerals from Bowen's reaction, what do they call that, series, the high iron comes out first, deeper, and then what's left at the surface is the low iron content granites. Would that do it? Sort of a complicated answer, isn't it? What's that?
Can we go over that again?
I can't hear.
Can we go over that answer again?
Okay. Let me see the question again.
The higher iron content, which is salt, comes out slower.
Okay, it comes out first. It comes, when the magma is cooling, the higher iron content has a higher solidification point, same as melting point. And so therefore, it comes out deeper into the Earth's interior. And then, as you get closer to the surface, but still intrusive igneous rock, most of the iron minerals have come out and have hardened already, and then at the very end, your light-colored rocks that are low in iron content, they come out at the coolest temperatures, so that would be closer to the surface. And that's from Bowen's reaction series. The reason for the fine grain of the basalts is that it's usually under the ocean floor, and that cools really quickly, but it's still deep. Bowen, B-O-W-E-N. It's on page, it's chapter 17, on page 444, top of the page. Probably it's top, yeah, it's on page 444. The graph is at the top of the page, and the description is near the bottom of the first column. And why they didn't flip that thing over. Because if you flipped it over, then you would have it would go going like this. And the darker stuff would come out at higher temperatures than the lighter stuff near the surface at cooler temperatures, and that would make a lot more sense. Because your temperature doesn't decrease as you go down, it decreases as you go up. So I don't know why they flipped it over like that. it wasn't particularly constructive. I didn't, instructive. Okay. Did I already return to two of the test fours? You got yours, okay.
Last one was good?
Yeah, I didn't return yours or Amber's because I think I hadn't finished writing those at the end of that period. So I think I gave you yours that was in front. Oh, good deal. First class to have all the papers in. That is fantastic.
Feel the pressure from these guys here.
Yeah, all right. When you run with a horseman, it speeds you up. Okay, so I think I've returned to you, not quite everything, but I'm still missing, I think, one lab. But when I get that, I can return it to you. Don't tell me I have these copies. Okay, I think I have the copies of the test in my office. I think I thought I had them in here with me, but I don't see them.
Invitation to include surveys, rocks used in building construction in your community. Football, other than woods. Man, ain't got no community. So this has got to be turned in along with those 15 questions. So we
Man, what 15?
Huh?
What 15 questions? That's very
back
easy.
to the chapter.
Hey.
Chapter 18.
Yeah, we do any 15 of those 20.
It ain't 15.
The other ones over there, those other 4.
Over here.
Yeah, you can choose
Over 20.
Oh,
16 plus 4. There's 20. Pick out 15.
give me an F on that. Marine work.
That will not work this summer. Teen's got 3 questions.
I couldn't find them, so I'm gonna have to go make more copies. Are y'all through? Or are you still discussing? Or disgusting? I mean,
We're done, but we were discussing these questions that were supposed to be.
okay. All right, well, I'll leave that on. I meant to turn it off before I went. Okay, what's your question there?
Oh no, we were just.
Oh, yeah, right.
Talking about how we didn't really.
Well, I can't believe that. And actually, you got plenty of time if you want to work on some of those questions, because they're part of the lab, but also because they're good things to study for the test. You can do that, or you can go and take the test. I can't find the copies I thought I had made, so I'm going to have to run more copies. So I've got to run down to the copy room. Well, no, I can just run across the hall here and get that done. So you got plenty of to work on while I'm doing, right?
So we can just write the answers down?
Yeah, right. Or, I mean, there's actually, isn't the back of the lab a blank sheet? You can put them there too, or notebook paper, whatever you want to do. You might need some more room, but if you do, go for it. Okay, I'm going to pause.